Okay. Okay, so coordinate geometry. I chose coordinate geometry because it's a topic that goes right the way through all the key stages from year 7 to A level. And every maths teacher at some way, shape or form comes across coordinate geometry. I also think it's quite a divisive and controversial one because I've personally completely changed the way I teach it about 3 times. And I've tried different things, and I'm kind of stuck on one that I like now and works for me at my school with my students. But part of what I'd like to do today is just to kind of share with you what I think is an alternative approach to teaching it, and that's the way that we do at Queen Mary's High School. It's not the way I used to teach it, as I said, when I worked in a comprehensive school for 10 years at Kingsmead Technology College, and I used a very different way of doing it then. Also, just to think that how does it work in your own school? That's kind of the part of it, is from year 7 to year 12. Does it blend from each year from one year group to the next and build on itself, or are there big leaps or big stumbling blocks that tend to work? And finally, is it a topic that's done consistently at your school, or is it a topic where everyone does it kind of their own way, and that helps blend and give students a more diverse learning experience? Or would a more consistent approach where everyone used the same method be beneficial for you? And those are all questions, not ascertaining one way is better than another. So when teaching coordinate geometry, it might be one of the first things to say is, what formulas do we as teachers normally give students and expect them to learn? And I'll just give you 20 seconds or so to see if you can count how many you might give students to learn right the way up to A level. And I've flicked on the slide there. At some point in my career, I would certainly have given an A-level student all 7 of these formulae. I would have talked about them, I'd have derived them, and I would have expected them to learn them. And most of the methods that I'm going to use today don't use any of these formula and don't really advocate learning the formula, perhaps generalizing to get to the formula, but not learning them. So I think it is quite a different method. So I'm going to start off in year 7. We're quite lucky, I suppose, because about 5 years ago, we rewrote our whole curriculum, and this was one of the topics that we really broke up into each year group as to what we're going to teach each time, so that it builds, and by the time they get to year 11 and 12, they'll be confident in the topic. So the whole of coordinate geometry was broken up, and in year 7, the real aim was to think what is an equation, to try and understand what it is, and to kind of start looking at some simple graphs. Now, I don't tend to use PowerPoints in my lessons at all, but when I teach year 7, this is how we do our first lessons on coordinate geometry. The first lesson is I give them a bunch of coordinates just like this, maybe broken up to 3 or 4 equations rather than 11, and just to ask them, can they see a pattern that links the 2 coordinates? Can they see a connection? And they discuss it and they talk about it, and usually they come up with ideas. And we can soon start generalizing, and we get things like y equals x add 2 come up. And another student might say the difference between them is 2. And we might even get x is y minus 2. And you might kind of think this is a bit strange, but it's flipping the topic on its head. Most often we teach it by giving an equation and then asking them to plot the graph. And this is a little bit the opposite. It's giving them bits of the graph and asking them to come up with an equation and to try and get the idea that there are lots of different forms that equations can be written in. And so yeah, so the bottom ones here, we've just done linear sequences, so the year 7s can start to make the connection between sequences and equations as well, which is sometimes a link that we're not able to make, and it really just depends on the classes and how good they are and how far they can be extended. But what we really want is things like the lines like this, where the y coordinates, so y is equal to 4 to be seen and really transparent, and x is equal to -3. And just to see that those are the equations and they come from coordinates. So that's our lesson 1. And if it's going well, we may spend a little bit longer. But moving on to the second lesson in the scheme, it's exactly the same really, except those coordinates, rather than being written in a list, are now written on a line. And somehow, students see graphs and they find working out the equation quite daunting sometimes, but it's exactly the same thing, picking a few coordinates out and then looking for a relationship between those values. And if the previous lesson's gone well, then all seems to go quite well again. I think I need to go back now to let somebody else in. So there we go. I've admitted somebody else. Hello, welcome to the meeting. Okay, so yeah, we look at all of those and they usually able to come up with equations that link all of those themselves, which if you think some year 11s find that kind of process quite hard because they've done so much more coordinate geometry, just given a line and being asked to say what the equation is quite difficult. But if they go back to the coordinates, they get a little bit more success. And then it's probably the more typical things for year 7 is giving them an equation like y equals 2x add 3, getting them to draw a table of values and then plot the graph. And we do get them to try and learn some simple forms and just do some matching. More so for when we get things like graphical inequalities, we really want them just to know those shapes rather than just be trying to work them out. And most of the students are able to do that fairly well. So that's our year 7. So we move off into year 8, and year 8 looks really heavy in our scheme of work with this, but most of the coordinate geometry is linked into other topics. So you've got changing the subject of a formula. That happens quite early on, and then obviously we move into changing equation forms into different equation forms and linking that to the graph. The Pythagoras we do in year 8, so finding the length of a line segment on a graph, midpoint, average x, average y, and that's the way we teach it. And it links quite nicely without giving the equation x1 plus x2 divided by 2. Obviously they can generalize those forms, but it's just average x, average y. We do ratio in year 8, so that links really nicely with gradient. And then forming simple equations where we know the intercept and talking about parallel lines, and then just extending the type of graphs we draw. So just to kind of give you a few types of year 8 questions we would get. So find the gradient of a line passing through points 2, 3 and 6, 9. This was quite controversial when we were talking about it as a department, because some people draw the line and some people don't draw the line, and some people draw coordinate axes and some people don't draw coordinate axes, and everyone was doing different things, and we wanted something consistent that they could just take through the school. So we said that we would draw a line segment, partly to get them just in the habit of drawing a graph, because as you'll know from difficult A-level questions, you have to draw it, and that should be one of the first things in a coordinate geometry question you consider doing. So in year 8, we do force them to draw it and to do their little bits of working. Oh, I should apologise for one more thing. I'm using a Wacom, and it's my 2nd week using a Wacom, and my writing is worse than my 5-year-old's, and I'm very self-conscious about it, but I get told if I practice it will get better. So I am persevering. So we would do things like that in year 8, and then try and develop a little bit more reasoning. So this is just a snapshot of a year 8 student work and some of the questions we might do. We never like them to write gradient using the letter M, because what you'll get in a case like this is M is equal to something, M is equal to something else, and then you've got a contradiction. So we try and push them to make full sentences and to say what they're doing, and to, where possible, label that line segment A, B, or with any appropriate letters that the question has. But I suppose rather than get difficult in year 8, we're looking for consistency of method and a good written kind of way of going through it. Exactly the same for the length of a line segment. So this would link with our Pythagoras topic, but they would say AB squared is 6 squared plus 4 squared, and then look to solve that as we normally would. But they've drawn their line segment, they've got those things. If they want to draw a little triangle, and same for all the gradient ones, some students like to see that. But we keep it consistent. Every coordinate geometry question, they draw the line segment. Find the midpoint, exactly the same. Midpoint is average x, 2 plus 6 over 2, average y, 3 plus 9 over 2. No formulas to be learnt. And in year 8, they become fairly good. Although it doesn't make any difference on their answers, we do push them to try and make the line orient in the right direction. So if it's clearly a negative gradient, then it works quite well. If I go back to one of the slides here, as a rule of thumb, if there are 3 coordinates or more, or 3 bits of information, often the coordinate axis is useful to draw, but just 2 bits of information, sometimes they get the intercept wrong and they're expecting it in a positive place or a negative place, and it doesn't work. So we do push for full coordinates to be drawn if there's lots of information, but little bits of information, just the line segment. And there, I've got a model solution for that one already. And we'd obviously get them to set the work out exactly like this and take little discussion points. So if I'm doing 3 minus 4, we wouldn't as a department at all want them to write 3 minus 4. That's just messy algebraically. We'd want them to do 3 add 4, it's 7. And when they work out the denominator, we talk that it could be 7 over minus 6, and that's fine. But as a convention, we put our negative in front of as a coefficient. So there's lots of kind of little bits of practice and algebraic intricacies as we go through an exercise for that. But they'll do questions like this in year 8. But nothing that's exceptionally unpleasant or difficult. What's the equation of the line there? So I'll move on to year 9 work. So year 9 is more formal in its methods, finding the equation of a line when you're given a gradient and a point, finding the equation of a line given 2 points, and little contextual situations are put as well. We try and interpret gradient a bit. There's a whole unit on looking at, say, if you've got a balloon inflating with its volume over time, what would the gradient represent at any given time? Not working out the instantaneous ones, that's year 11, but just interpreting what gradients mean. We also show them the x is 0, y equals 0 method for drawing a straight line. When you've got equations in, say, that form, 2x plus 3y is 12, we'd recommend just making x equals 0 and getting 2 coordinates and joining them together, and that links well to graphical inequalities. So that's our year 9. Now this is where I think the method probably diverges most from a method that's more commonly taught, so I'll be quite careful. So find the equation of the line passing through 3 minus 4 parallel with, well, there shouldn't be the word parallel there, my apologies, with gradient 2. So we draw the line segment, and the students immediately recognise, oh, we don't know what this top point is here. Every time in gradient problems up to now, we've had that. So we can just put a general point, x, y. And if we do that, we can then say the gradient of this, y plus 4 over x minus 3 is equal to 2. And I like to say to the students at that point, we now have the equation of a line. We've solved the question. We've essentially found the equation. And it doesn't take long for people to say, oh, but it's not normally in that form. We don't normally see them like that. And then we practice, and this is where students most commonly go wrong. It's in the actual process of doing the expansion, especially if there's a negative in front. But I like to stress that the equation is actually here. We found the equation. Now we're just manipulating the algebra. And as students continue this into year 12, they become, oh my goodness, we become better and better at not making mistakes like I just did there. But yeah, that's one of the year 9 problems we'd be looking at. Kind of getting a little bit more involved, find the equation of a line passing through parallel. So I've modelled this one already. When we do this, we do insist that students check their answer, so we know that coordinate, so then you can plug that into to find out if it does indeed satisfy. So that's year 9 as well, and I've taken some photos of some year 9 work and how we would want students to lay it out. We do a lot of time in year 8 on algebraic fractions like this, and how to deal with them by cross multiplying. So students are quite adept at that, and as soon as they get through that step, the simplification tends to go fairly well. It's more the reasoning side where students go wrong rather than the standard questions. So here's another one. Find the equation of a line passing through 2, 3 and 6, 9. Now I know the way I used to teach this was y minus y1 over x minus x1 is y2 minus y1 over x2 minus x1, and I certainly wouldn't in year 9 want to be doing anything like that. Instead, what we do is we put a general point on xy, because we've learned that idea that a general point creates an equation. Y minus 3 over x minus 2 is equal to 9 minus 3 over 6 minus 2. And there we have the equation. The students, again, they accept it. They're quite happy they found the equation, but they want to clear it up and tidy it up as we should do. And you know, that's where the mistakes come. It's the actual generating the equation itself is so easy by the method, but y minus 3 over x minus 2 is equal to 6 over 4. We always simplify fractions before we cross multiply. X minus 2 is 3 over 2. 2y minus 3 is 3x minus 2. 2y minus 6 is 3x minus 6. So 2y is equal to 3x. Have I made a mistake there? Whether I have or I haven't, the method still holds, and I could check it by making a substitution of one of my points. And actually, no, it looks quite nice to me. So that would be some student work that we would take from there on that topic. And again, how much they need to practice kind of depends on the students. Some of the weaker students just need to repeat the method until they get, which is all good practice of their algebra. So I've got no real qualms of doing repetitive practice for it. But obviously the better students are ready for more reasoning type questions fairly soon. So that's our year 9 scheme done and dusted. And usually we're okay then. There's no major difficulties. In year 10, there's more reasoning. We introduce perpendicular lines. We talk about tangents and perpendicular bisectors. And if students have poor recall of their year 9, they need a lot of differentiation and support going back and kind of redoing some of those problems. And usually in year 10, one of the first lessons does involve just giving some repetitive year 9 practice so it goes back. But we're looking for tangents to circles and perpendicular bisectors, and there's any kind of major differences in the way we teach this here, except I think this is the most challenging, because when you're teaching bits of this, some students are ready for it and some students need scaffolding. And I have done that before with tangents to circles, is almost given them a scaffolding sheet with prompts or a worked example for weaker students, so that they can follow that as they go through. Usually in year 10, we do an investigation, which again, I apologise if I'm speaking and you know of this one, but it's a really beautiful investigation. If you've got a circle that comes, especially from a Pythagorean triple and a general point, so it's a 3, 4, 5, that when you put those into the equation, when you find the tangent by the usual method, find the gradient to the radius, the gradient to the tangent, and then your coordinate geometry, the coefficients here stand out as being the point. So you might try with minus 3, 4 next, or you might do a 5, 12, 13, or a 6, 8, 10, so 6, 8, 100 would be the circle, and see if you can get them to generalize themselves. And it's a good way to get them to practice it, but also to try and generalize. If students are quite exceptional at this, we do then look if a line meets a tangent, or perhaps it could be a chord, or perhaps it doesn't intersect at all. in one of the Edexcel papers within the last 3 years, there was a question where it looked exactly like coordinate geometry, but it was simultaneous equations. You had to prove it was a tangent, and you subbed your equation back into this equation, and you saw that there was just one root, which was a really nice question. But since then, we kind of link simultaneous equations and coordinate geometry a little bit. So then comes to year 11, and this is kind of, I suppose, the happy stage if it's all gone to plan up till now, and that you're able just to look at exam style questions, and perhaps some of the more geometry style ones. You're able to go back for students who have missed bits or not understood bits, and support them and try and get them up to scratch. I'm not saying that every student at the school is brilliant at coordinate geometry in year 11. Far from it, I wish they were. But a lot more students are now able to access it than they were before. And also we get good, if you look at the coordinate geometry A-level units, the students that we've taken through the school, and we've had 5 years now following this, tend to be quite successful. Some of the questions we might look into year 11 is a bit more of the actual geometry things. There's some nice things to do with quadrilaterals, like the diagonals of a kite are perpendicular. So I've got a little question down at the bottom, which I always give them in year 11. Prove vertices form a kite, and they kind of understand a little bit more about quadrilaterals, and I've given some more properties of parallelograms and rectangles, and their diagonals, which makes some nice results for coordinate geometry. And then A-level, there's not really an awful lot more. There's linear modelling, and then you can move on to circles and calculus before long. And we use exactly the same methods right the way through. I know it was one issue I think I had in my last school more, is that we always used y equals mx plus c at GCSE, and then suddenly moved to y minus y1 equals mx minus x1 at A-level, and students didn't transition well. Some of them wanted to keep to the method they used before. So generally we never change methods throughout the 7-year cycle. We try and keep the same ones throughout. So I've presented all of our 7-year curriculum without any of these formulas. Although I would say in most exercises I would get students to derive the formulas and to show that they are general formulas, you know, especially that one, they all work very nicely. If you take the line, let's say we take this formula here and we take that line there with our general point x, y, and we've got x1, y1, and x2, y2, you very quickly come to that, so it works quite nicely. I know for a matter of fact, before I was shown this method, I would have been very cynical about it. So I wanted to do one question and show you 3 different ways of doing it, where maybe the pros and cons can be looked at for them. So find the equation of a line passing through 5 minus 2 with gradient 2/3. This is the traditional method at GCSE. It's definitely the one used in Hegarty Maths and My Maths. The CGP textbook teaches that. And I think there is one real benefit from it, and that is that you get this gradient in there really, really quickly, and you get one easy mark. And for students who perhaps aren't always able to get the full way, I think there is a real benefit in teaching this, because it gives them the one easy mark. This was the method that I would have definitely taught up to A-level, and it mirrors this very, very well. The only difference is there's no real remembering of a formula, so you just have that general form. The gradient is 2/3. So they're there to be compared. Hopefully I've put some things that are a little bit controversial and challenging, really. That's kind of the idea, rather than tell people stuff that they're already doing, and hopefully that will spark off some conversation in your departments as to whether you like it or whether you hate it, or whether what you do is consistent through the school and whether it works, or whether actually having lack of consistency and everyone does something slightly different kind of enriches the experience of the students. So that is